All right, so we start off with 22 moles of water. 22 moles of H2O, and what's my next step? Mole to mole ratio, good. So what goes on bottom? 6 moles of H2O, make sure you put the moles. So 6 mole of H2O came from the balanced equation. I'm going to put that on there. Came from the balanced equation coefficient. That's where that came from. And what goes on top? Who are you trying to find? Aluminum hydroxide. So what goes on top? 2 moles of aluminum hydroxide. Good. And is that what you're trying to find? So you're done. Make it simple. Don't go to grams. This problem said nothing about grams. So a third of 22, what is that? 7.33? So, and that would be the correct significant figure. So 7.33 moles of AlOH3. Yes or no?
Yes, miss.
Does it make sense? Okay, the next one. Is the next problem a limiting reactant stoichiometry problem or not? Yes or no? No, it is not. It is not. So what are we starting with? 2.50 moles of who? All right. So write that down. Now, I'm going to be quiet and see if you can do this one. What's that next step? What's the next step? Everybody should tell me. What's the next step? Mole to mole ratio, good. Where does that come from? Coefficients, good job. I want you to try to do it without me writing the next step. You write the next step. I'm going to be behind you. I want to stay behind you this time. I want you to do the next step before I write it. Look at what you're trying to find. What are you trying to find? What does it say to find? Pounds of who? Are we in aluminum sulfate now? Yes, so we're in aluminum sulfate. How do you get to a mass from moles? Periodic table, but have I given it to you in the problem? Have I given it to you underneath the balanced equation? So use what I gave you and look at the units. I put the units for you. What are those units?
What is it for aluminum sulfate?
It's on there. It's on your paper. Nobody has it down there? It's 342.17 grams per mole. 342.17 grams per mole. And then you should be able to do the last step, because the last step is converting grams to what? Pounds. So do grams to pounds. How many grams are in a pound? 454 grams in 1 pound. All right, run your numbers. How many significant digits should you have in your final answer? So what's my final answer? 0.628 pounds Al2SO43. Good job. Yes or no? Is this making sense to everybody today? All right. The next problem, is that a limiting reactant stoichiometry problem? No, it is not. How do you know? There's not two givens. There's only one given. Good job.
I got stuck on a homework problem with that. I was like, what do I do when it finally hit me?
We sometimes make them too hard, and sometimes they're too easy. I mean, sometimes it's like we think we have to go do something else that we don't need to do. Like in this case, where are you going to stop this time? Moles. So make sure you stop at moles. Make sure you stop at moles. So put the given. Now I'll slide it down so you can see the balanced equation up there. You're stopping at moles of sulfuric acid. So those of you that don't have the paper can see this.
What element are we stopping on?
Sulfuric acid, moles of sulfuric acid. All right, what do I put on top? 1 mole of who? Aluminum hydroxide, good job. What goes on bottom?
78.01 grams.
Good. And then what's my last step?
2 moles.
Mole to mole ratio, what goes on top?
3 moles.
3 moles of sulfuric acid. And what goes on bottom?
2 moles.
Aluminum hydroxide, good job. What did you say again?
0.072 moles.
How many significant digits are you supposed to have? That's not 3. Zeros in front of non-zero digits are not significant. So what's the answer? 0.0721 moles of H2SO4, or 7.21 times 10 to the negative 2 moles H2SO4. Either one is fine. Yes or no? That's probably one of the most missed significant figure errors, because people forget that that zero is not significant. A lot of the mistakes on the Achieve homework are because of significant figures, something like that.
Just after it.
Say that again.
Or isn't it the zero just after the number?
If there had been a zero here, this would have been significant, but the zero in front is not. It's in front of non-zero digits. Zeros in front of non-zero digits are not significant. Zeros at the end of a number that includes a decimal are significant.
Okay. So if it was 1.0721, would that zero still be
1.0721, absolutely. Anytime the zero's in between, it's significant. If it's sandwiched, it's significant. Other questions? All right, I'm overloading you with practice on this, so hopefully you do well in the test for this, and you've got lots of practice on Blackboard. All right, both of these questions are what? Limiting reactant problems. So I'm going to be quiet, and I'm going to leave these up here and let you do them for a bit. And I want you to do them. Do not wait for me to do it. Every one of you have the previous page. The top problem on the previous page has all of this. So flip that back and do them. Thank you. Try to get both of those done, guys. All right, guys, I'm going to give you just a couple more minutes. Okay, so let's get going on these. Let's see what we can do. All right, so is this a limiting reactant problem? Yes. So we have two givens. So 2.50 moles SO2. The second given is 2.50 moles of O2. Yes or no? Okay. All right. Once you're in moles, what's the immediate next step? What are you ready for? Mole to mole ratio. All right. So we're ready for the mole to mole ratio. So we get that from the coefficients. We want to get out of SO2. So it's 2 moles of SO2 on the bottom. And we want to be in sulfuric acid. So it's 2 moles of H2SO4 on top. Yes or no? All right, so moles SO2 cancel. It wants to know grams of sulfuric acid. So I didn't give it to you this time. So you have to go figure this out. So it's 2 times 1.01 plus 1 times 32.07 plus 4 times 16.00. So you've got to figure that out. If my memory says correctly, it's 98.09. Is that right? Is that right?
Yeah.
Okay. All right, so 98.09 grams H2SO4 over 1 mole H2SO4. Is that what we want to be? Yes. So moles of H2SO4 cancel out. I could also cancel those 2's out. So then plug in your numbers. And the significant figures should be how many? So what's my final answer here for this problem? 245 grams H2SO4. Now that may or may not be my final answer, so I'm just going to stop right there. I could underline it, but I'm not going to circle it yet. Yes or no? All right, the second problem. The second problem. What are we ready for? Mole to mole ratio. So I go to my balanced equation. How many moles of O2? 1. So 1 mole of O2 on the bottom. What comes on top? What are we trying to find? Who are we trying to find again? Sulfuric acid. So what is that? 2 moles of H2SO4. So moles of O2 cancel. I'm in moles of H2SO4. What do I want to be in? Grams. Is my last step exactly the same last step as before? Yes. So 98.09 grams H2SO4 over 1 mole of H2SO4. What? Not a line. Equals. So mole H2SO4 cancel. Plug in my numbers. And if you know math, you know it's going to be doubled what the other problem was. So 490 with a decimal grams H2SO4 because of significant digits. Yes or no? Now, my final answer is which of those? The smallest. Because how much can you produce? The smallest amount. That's what you produce, is the smallest amount. Now, which of these is the limiting reactant? How much though? You got to tell me how much. 2.5 moles of SO2. So this is the limiting reactant. And the reason I'm being very specific and adamant about you have to tell me how much. What if I had 10 moles of SO2? Would that be your limiting reactant then? Could you say it was moles of SO2 as my limiting reactant then? No, it's the quantity that's the limiting. It's the quantity that makes it limiting. So 2.5 moles of SO2 is my limiting reactant. Which of these is my excess reactant? The 2.5 moles of O2. Now, there is a question in your homework, I believe, that says how much excess reactant is there? How much is unreacted? How much excess reactant is left over? How do you figure that out? Well, you don't just subtract these numbers, because these numbers are the actual product formed. Well, in a sense it's a ratio, but go ahead and do it as a stoichiometry problem. Do it as a stoichiometry problem. What you will do is, once you know who the limiting reactant is, you have to solve for who the limiting reactant is. You have to figure out which one is excess. So in this case, if we wanted to know, and I'll do it down here. I'll do that question that I'm going to ask, and I'm going to make a note of what the question is down here. How much excess reactant is left over? How much excess reactant is left over? So what you have to find out is, how much excess reactant did you need? Does that make sense? Do you have an amount of reactant? How much reactant did you have to begin with? 2.5 moles. And that's excess, yes? So that's too much. So you have to find out, well, how much do you need? How you find out how much you need is you solve for the excess reactant, moles of O2, using the limiting reactant. So you're going to start with the limiting reactant. So start with limiting reactant. Start with limiting reactant and solve for excess reactant. Then take the difference. And I'll do it. So in this problem, who was the limiting reactant? 2.50 moles of who? SO2. So who are we going to solve for? Not grams. We don't need grams of O2. Look, it's moles. It starts in moles, so we just have to go to moles. So we're going to go to moles of O2. So go to your balanced equation. What goes on bottom? 2 moles of SO2. What goes on top? 1 mole of O2. So 2.5 divided by 2, that's 1.25, isn't it? So that means we need 1.250 moles of O2 needed to perfectly react with 2.50 moles of SO2. Does that make sense to you? You need 1.250 moles of O2 to perfectly react with 2.5 moles of SO2. Then you would have nothing left over. That would be the perfect reaction quantities. But how much do you have? You have 2.50 moles of O2, so how much excess do you have? 1.25 moles of excess. So what you're going to do then, the difference is 2.50 moles O2 have minus 1.25 moles O2 needed. That equals 1.25 moles of O2 excess. Follow? Isn't that neat to be able to figure that out? It took you a little extra steps, though. You got to think about it. And that's why I threw that one on there, to make you think. And some of you did. Some of you emailed me, and I was able to tell you what I just said right there, basically. And you're like, yeah, I got it. So good job, whoever that was. Good job. Is that one of you all? Okay. Yeah. Does that make sense?
So it's basically getting it using basically doing the multiple ratio.
Well, in this case, that's all we had to do. But don't say it's always going to be just a mole-to-mole ratio. It's solving for the reactant. It's taking, because it could have been in moles. It could have been grams. In this case, it just happened to be in moles, so all we had to do was a mole-to-mole ratio. What you're doing, though, is you're solving using the limiting reactant, solving for the excess reactant. So you're solving with a reactant to a reactant. You are doing similar to what we did above, but we're not trying to find grams of anything in this particular situation. Had we started in grams, had these been in grams to begin with, then yes, we would have had to go to grams, but they weren't. Okay? All right, have you got the other problem done? You had enough time, hopefully you did. So let's look at it. Is this a limiting reactant problem? So how many problems do we have? Two problems. So what's one given? 2.0 grams of SO2. And the other is 10 grams of O2. Yes or no? All right, what are we solving grams of SO2 to? Moles. So is that 40, what is that, 30? 64.07, isn't it? So 64.07 grams in every 1 mole of SO2. Grams cancel. What's my next step? What's it called? All right, so I go to my balanced equation, and 2 moles of SO2 on bottom. I'm trying to find sulfuric acid, so that's 2 moles of H2SO4 on top. And then I want to have grams of sulfuric acid, and I've already calculated that above, so 98.09 grams of H2SO4 over 1 mole. Moles H2SO4 cancel. My 2's cancel. Run your numbers. And I get 3.1 grams H2SO4. Yes or no?
Yes.
Okay. 2 significant digits. That's all we had here. Yes, no? Makes sense? All right. 10 grams of O2. So that's going to be 32.00 grams for every 1 mole of O2. From my balanced equation, that's 1 mole of O2, 2 moles of H2SO4, 98.09 grams of H2SO4 for every 1 mole. All right, gotta check you. All right, so it's 3 significant digits on this one. So it is 61.3 grams H2SO4, and I made that one way too easy. So what's my final answer? 3.1 grams H2SO4. So that final answer.
I don't know, it's pretty close.
It is close. I mean, I take a while. I usually try not to give you, oftentimes, and I didn't do it well on this page. Well, on this one, it was okay. This one, I like to either give you the same quantities of reactants so that you have no idea and you can't even guess because you've got to do the problem to figure it out. Or I often like to, when I know this is going to be the answer, then I like to give if it's possible, I like to give the limiting reactant to be in greater quantity to start with than the excess reactant. So that you get, because so much of the time students will be like, oh, well, that one's smaller, it's going to be that one. And it did work out to be that this time, but does that have anything to do with anything? Does it really matter what you start off with? No, but when you get a problem like this one, people think that. And that's what always scares me. I don't ever want you to get into the habit of just thinking, okay, that's the smallest one, that's going to be the limiting reactant for sure. No, it's not. No, it's not. Okay? All right, yes or no on this? Okay, thus ends the test material for test 3. So let's look at this little note down at the bottom. It says test 3, equations and reactions, balancing, writing balanced equations from word equations, predicting products, type of reaction, stoichiometry problems, limiting reactant stoichiometry in addition to just regular stoichiometry, and then mole, gram, atom, molecule, formula unit, Avogadro number, dimensional analysis problems, percent composition, empirical molecular formula problems. And guys, there is so much practice on Blackboard. If you go down under that practice problems and scroll all the way down toward the bottom, it'll say all test 3. Yes?
Are we ever going to have a because you said assume.
I said you could have one. I would have to tell you it's incomplete combustion. I don't know. I might. I don't know. But if I do say it's incomplete combustion, instead of getting CO2, what do you get? CO. CO. If it's incomplete combustion, then it's going to give you CO. It's going to give you CO, not CO2. Okay, what are your questions? If you do all the practice problems that are on Blackboard and you know how to do them without looking at the answer key, you will ace this test. But if you don't practice and you just come to class, you're listening and you're copying down what I write, you're going to fail the test. Because you can't, it's a lot of math. And it's a lot of nomenclature. It's a lot of nomenclature if you don't know your ions. Okay? So talk to me. Ask me right now anything you want to know about the test. Yes, sir.
Could you go over percent composition?
Yes, that's why I brought my book. Yeah. Actually, I'll look. I've got all my notes too. So I'm going to start with my notes, and then if I need to, I'll try to pull some other problems. All right, so if you've got your notes that start with moles, this is the back or the bottom. This is where we started with percent composition. And if I remember correctly, this lecture was split over 2 different days, which may be part of the issue. I remember this being 2 different days. I told you one way to do it, which was the easier way, which was on the second page, and then I came back and did this way. So percent composition, there's 2 different ways to calculate percent composition. One way is if a formula is given to you. If a formula is given to you, then you are going to basically look at the formula and you take the number of atoms of the element times the atomic mass of the element, which this all comes from the periodic table, divided by the formula mass of the compound times 100. And so in this case, I did an example for you. H2O is water. So we have a formula for water, and then it says find the percent of hydrogen. So how many hydrogen atoms do we have? 2. So you have 2 hydrogen atoms. That's where this 2 comes from. What is the 1.01, the atomic mass of the element? Is that the atomic mass of hydrogen from the periodic table? Yep. And then you divide that whole thing by 18.02, which is the mass of H2O, times 100, and you get 11.2%. Now, let's do another one. Okay? let's do one that's from one of these problems that we just did. So H2SO4, I want to know the percent sulfur. H2SO4, the percent sulfur. So percent sulfur equals, how many atoms of sulfur do we have? 1. So 1 times, what is sulfur's mass? Go ahead. 32.07 grams per mole. And you don't have to put units because your unit's going to end up canceling out, but it's okay if you do. That's usually not what I say. I usually say put units, but here it doesn't matter. All right, what is the molar mass of H2SO4? You've already calculated it today. 98.09 grams per mole. So 98.09 grams per mole times 100 equals, so your grams per mole cancel, so then it's 32.07 divided by 98.09, and so you end up with how many significant digits? You have to base it on these masses, so what would that be? 4, so my final answer is 32.69% sulfur. Yes or no? Okay. Let's do another one. These are I always love to do these. So it's fertilizer time. And for me, it's so funny because whenever I always go to figure out how much fertilizer I want to put on my field, I use this information basically. And I always ask them, I'm always making sure I know the prices and all that and checking around, but I always want to get to the exact pound, which is kind of silly because, the trucks aren't that efficient to pound. I mean, they say they are, but where I get my fertilizer, they're probably not. But it's okay, I'm still going to be me and keep doing this. So every year when I get ready to do fertilizer, I have a dimensional analysis, little paper that I do my little dimensional analysis on to do my fertilizers, knowing how many acres I have. And so one of the things I want to because some of you are ag majors, some of you are going to deal with this, okay? That's why I'm telling you this. It's percentages, but it's slightly done differently, so don't get confused for a test, okay? I need to talk to real life for a minute. Don't get confused on your test. So let's take, for instance, I'm going to do one that is your test. What is a source of fertilizer that's used for nitrogen? It's not used commonly anymore, but what is a source of fertilizer? You can tell me any source of nitrogen. Say it. Ammonia, anhydrous ammonia, which is what? What's the formula for anhydrous ammonia? NH3. That's ammonia. Anhydrous ammonia is NH3. Okay, does anybody know the numbers for NH3? So it'd be something 00. Like DAP is, anybody know DAP? What are DAP numbers? 1846O. Potash is 0,060. Here, let's do a little real life. It's NPK. Nitrogen, phosphorus, potassium. That's when everybody talks about fertilizer. This is off a little bit, okay? This is real world. You need to know these things. If you're an ag major, you cannot leave this classroom not knowing how to apply chemistry to ag, okay? If you're not an ag major, you have a yard. Some of you will over-fertilize your yard. Don't do that, okay? It just makes you have to mow the grass. Don't do that, all right? So NPK. So urea is a common source of nitrogen. It is 4600. That means it has no what in it? Phosphorus or potassium. DAP, which they call diammonium phosphate, which is not a proper chemical name, has both nitrogen and phosphorus, but no potassium. What they call potash is no nitrogen, no phosphorus, and 60% potassium. So these numbers are the percentages of the element. That's what those numbers are. So those numbers are the percentages of element. So if urea is, and in this order, NPK, so it's 46% nitrogen, no phosphorus, no potassium. DAP is 18% nitrogen, 46% phosphorus, and 0% potassium. Potash is 0% nitrogen, 0% phosphorus, and 60% potassium. So now there's two more forms. So urea is what you would be putting on right now if you had a pasture or hay field. That's what you're going to be putting on. It's a granular. Urea is granular, and that's what you're going to be putting on right now. That's the most common form of nitrogen, source of nitrogen right now. If you are a row crop farmer, then you may use, in addition to urea, throughout the season, you may actually use what's called anhydrous ammonia. And that's what we were talking about earlier. So anhydrous ammonia is NH3. That's ammonia. It's extremely hygroscopic, meaning attracting water. Extremely water attracting. And as soon as it mixes with water, it becomes ammonium hydroxide. In lab, when we had experiments that said use ammonia, it was actually ammonium hydroxide that you were using because it was already mixed with water. Why is it so dangerous to use ammonia? Say that again?
You know, like freezing, like
It's not freezing you, it actually is burning. It burns. Because if you are ever at the back end of an anhydrous ammonia tank, whenever things are getting hooked up, and if there's any kind of leak, as soon as that anhydrous ammonia comes out, it's going to seek water. Now, where's the water in your face? Eyes and nose and mouth. So it will fry you. It will dehydrate. I shouldn't say fry. It actually dehydrates. That's what a burn is. A burn is dehydration. That's what a burn is. And so it will go and it will absorb your water in your nostrils and in your eyes, and that is seriously very, very, very dangerous. It's very dangerous. And so that's why you have to be very careful. So when you guys are driving this spring and you're driving behind an anhydrous ammonia tank and you see this truck or tractor with this tank behind it and you're in a hurry, just chill your bones and chill out and slow down, because they don't want to get in a hurry and you don't want them to get in a hurry, because if that turns over and causes it to leak, guess who's going to be hurt? You. Okay? And whoever else is in the vicinity, because if that thing blows, then it's going to affect everybody around it, not just one person. Okay? And so chill your bones and just relax. Okay? It's providing food for you. So those are things that we can know. Now let's take this. Did I give you the NPK for ammonia? No. Now you figure the NPK for ammonia. When I mean that, I'm saying you figure out how much nitrogen is in ammonia. Give me the percentage of nitrogen in ammonia. Give me the percentage of nitrogen in ammonia. And what do you get? 82.22% in. So is that a very good source of nitrogen? Is that a really good source of nitrogen? Yes, that's a very good source of nitrogen. The problem with it, it's obviously it can be dangerous and it's also very volatile. It's very volatile. And so this is the one that's usually injected into the ground. It's actually inserted into the ground because otherwise if it's just laid on top and it's blown down, what's it going to do? It's going to evaporate and it's not going to get where it needs to go. So this one is actually injected into the ground. So if we were writing the NPK for this, how would it probably be written? If you were writing NPK for this one, how would you write it? Come on. 8200? Does that make sense? Okay. All right. Now, how, and this has nothing to do with the test. I just want to teach you something. How would I use these numbers to calculate how much of these I need to put on my field? Well, what do any of these numbers mean? This means 82%, but what does a percent mean out of 100? 82% means 82 out of 100. So can I put that into pounds? So if I have 100 pounds of one of these fertilizers, let's say I have 100 pounds of urea, how many pounds of nitrogen do I have? Does that make sense? So if I need to put down, let's say that my soil test says that I need to put down 100 pounds per acre of nitrogen. That's what the soil test says. Soil test says I need 100 pounds per nitrogen, 100 pounds of nitrogen rather per acre. And I have 32 acres. This is what's written at my house right now. I have 32 acres. And I need 100 pounds of nitrogen per acre. Then I'm going to use what? If I only wanted to put nitrogen down, what would I probably use? Urea. I would be using urea. I would not be using ammonium or ammonia. I would not use anhydrous ammonia. I would be using urea because that's what's common now. So what do I know? What's my soil test say? What's my soil test tell me I need? 100 pounds of nitrogen per acre. So I would say 100 pounds of nitrogen per 1 acre is what I need. This is what I need on soil test. But how is it provided to me? What is urea? I wrote it down up here. What's urea? 4600. What does that mean? 46 pounds of actual nitrogen per 100 pounds of urea. Does that make sense?
Yep.
That's what that means. That's what that percentage, the numbers mean. So now, run your numbers. 32 times 100 times 100 divided by 46. And lots of times these are done in tons, so let's go ahead and do it in tons. So what do I need? How many tons of urea do I need? 3.5 tons of urea. 3.5 tons of urea. Now, if I had stopped at pounds, that's how they're going to set their fertilizer spreader. Because if they stop at pounds, the pounds was 6,956, and it's over, so that was total pounds over 32 acres. So then they're going to figure, they're going to need to spread it at 217 pounds per acre. So they're going to have to set their thing, or they're going to have to double spread depending on how much they can spread per acre. If they can only spread 100 pounds per acre, then they're going to have to double spread it. Does that make sense on what's real life, how you would use those? Now, what I also do is I throw in one more column. I'll actually do my problem, and I'll do what I tell you not to. I'll stop and start. Because I've got to be able to tell my lady when I call in for the fertilizer, I'm going to tell her, I'm like, okay, Ruth, I need this many pounds. And so I call her and I tell her how many pounds, but I already have figured out how much it's going to cost me. Because all this is based on, can I afford it? Can I afford to do this? And so the last column is, the last little set of dimensional analysis is going to be, how much does that urea cost per ton? And so that last column is going to be the price per ton, and I already know how much that is. Now, what if I was also going to put on DAP? Look at DAP up here. Does it already have some nitrogen in it? So would I be putting on this much urea? No. I would actually first figure my DAP, how much phosphorus I need on my field. Then I would figure out how much nitrogen I'm getting out of that quantity of phosphorus, and then subtract that from how much urea I need. So these are real world. This is what you do for real world. Okay? You all are ready to go. That was way more than you asked for. Did I answer the question you were asking for? Now wait, guys, I didn't answer every question, so hold on a minute hold on. I want to go back to one thing before we leave, because I only answered part of his question. I answered beyond his question, but I only answered part of his question. There's another way to figure out percent composition. If I give you real numbers. Do you remember this? No, not on this. Not on this. That is for empirical molecular formulas. You assume 100. For percent composition, you can have actual data. So if I give you actual data, so like it says, suppose 0.358 grams of sample of chromium reacts with oxygen to form 0.523 grams of metal oxide. What is the mass percent of chromium? So you take the actual amount of chromium, divide it by the actual amount of compound, times 100. Now, sometimes you've got to subtract. So like in this problem, it said a compound made up of 13.43 grams of aluminum, and the remainder is chlorine. The total amount of compound is 66.61 grams of total compound. If you want to know the percent of chlorine, what do you have to do? You have to subtract the grams of the compound, grams of aluminum from the grams of the compound, and what is that? The grams of chlorine? And then divide that by the grams of compound total times 100. Do you remember that? Okay. Guys, if you don't have these notes, you've got a video of it, okay? All right, other questions? Guys, be quiet a minute, please.
The soil parts,
What now, bud?
the parts you did with like the NPK.
That's not on your test, honey. That's on your test. But you have a question? That's not on your test. That's why I said it. That's not on your test. The NPK stuff is not on your test. That's how to apply what we've been learning to real world. But I'm not going to test you on that, okay? Other questions? Okay. All right. I will see you on Thursday. Lucas, Katie, and Ryan, come see me real quick.